Hello, everyone, and welcome to the Hyperthesis podcast, episode number 69. Nice. I'm Patrick.
I'm Pheely.
I'm Liam.
And I'm David.
Well, as you can hear, we have a guest on our show today. This is David Kunar, a PhD candidate in Crystalline Material Chemistry, who's working with Dr. Peng Wang at Queen's University. We will learn more about David and his research and his dreams and aspirations possibly later on. But for now, if anyone has an intro topic, which I do, we'll talk about it quickly. And so for today's intro topic, I want to talk about hail. So I was at a very interesting talk last week from a professor from the University of Western Ontario, also known as Western University, who gave a very interesting talk about hail. So hail is the chunks of ice that fall from the sky, typically during some sort of thunderstorm or convective storm, as they're known as. And it turns out we do not know a lot about hail whatsoever. And it's nice because in Alberta, where I'm located, but not quite where I'm located, we actually get some of the most hail out of anywhere in Canada and even North America. And it's just because we have kind of perfect conditions in kind of the southwestern region of Alberta that lends itself to creating a lot of hail.
One strange thing about hail is that compared to snow, I think hail doesn't need to be that cold. I remember in my country, we used to have hail, but we never have snow. That's interesting.
Yeah. So just as a little background about hail before we get into what this talk was about, one can be warm for it, even though hail is ice.
Is it because the hail falls faster than the snow does and doesn't have time to melt sufficiently?
Something like that. So traditional thinking is that hail is formed in these convective storms. So you have a lot of updrafts occurring. And when these updrafts are essentially pushing upwards against precipitation, whether it be ice or snow that's formed in kind of the upper part of the troposphere, it pushes it up. And then more water is able to freeze on it because it is quite cold up there. Even if it might be, say, 30 degrees down on the ground, saying Thailand, it might be still negatives up that high. And so you get this essentially frozen clump. And as the updrafts continue to push it up, it will freeze some more. And then freeze some more. It will just kind of keep pushing up until it's either heavy enough to overcome those updrafts or those updrafts disappear and it falls to the earth in the form of hail. And so it's really cool when you cut open a piece of hail, you see these layers, almost like a jawbreaker, if you've ever had those candies.
Like ogres.
Yeah, that's what I was going to say.
Yes, like an onion or an ogre.
Right.
So they have a lot of layers, and these layers are from that formation of essentially going through areas of wetness that then freezes on top, and then just doing that continuously. And now hail, if you've ever experienced it, which I'm sure most people have at some point, is usually quite tiny. So it might be, say, the size of, I don't know, a small pebble or even smaller than that. But the nice thing is, or the not nice thing is, in southern Alberta especially, there's an area known as the Hail Belt or Hail Alley, in which there's quite a bit of hail formation because you have mountains with winds blowing to the east that cause these giant updrafts that form this hail. And so it will fall to the earth, and instead of being pebble-sized, it's tennis ball-sized or softball-sized. So it can get quite large, and the person giving the presentation actually had a 3D printed hailstone that is the largest one on record. So they actually took it in, made sure it stayed cool so it didn't melt at all, scanned it, and then 3D printed it. And it was like a good sized chunk, maybe half the size of a standard brick that you might find.
Well, I wonder if they study the crystalline structure of those hail. Are they hexagonal ice or are they a different crystal of ice?
That's a good question. And I'm curious if there are any studies. But this group, they were more so focusing on trying to predict when hail would be coming and how it's formed, not so much at the molecular level, but they're interested in studying, okay, what are the mechanics that actually form hail and determine its size, whether it's going to be pebble sized or softball sized. And that has a great determination in the amount of damage it does. Because I believe Calgary in 2020, during that summer, had the first $1 billion, at least in terms of insurance claims and damages. It was the first over $1 billion hailstorm within the history of Canada, at the very least. So lots of damage, especially if those stones are bigger. And there are a lot of other unknowns about it. So how does it fall? Because hail can fall from anywhere within a strip that's a couple 100 meters wide to a couple kilometers wide. So there's a lot of variability in how hail is formed and how it falls. So there's a very large team that's being led by doctors Greg Kopp and Julian Brimelow, who was the one that gave the talk. And it just started 2 years ago now, I guess, in early 2022. And they're trying to study essentially all aspects of hailstorms, whether it's its formation up in the clouds or how it falls, because they're still trying to determine how it falls and the impact that that can have. Also, hail size and its distribution, and trying to predict that using a whole bunch of different methods.
This reminds me of when people study plastic in the ocean, especially oceanic garbage, where sometimes when you have a plastic that you drop, let's say on the beach, right, and somehow it ends up thousands of miles away, and sometimes people think, oh, it's like a chaotic system where you can't really predict it, but people do study it though. If you put enough trackers, like a buoy tag trackers, so you see the trajectory of each garbage or the tracker, and it turns out that actually a bunch of like belts of garbage in the ocean that they found is form kind of like the stable point in the kind of this kind of very high dimensional complex system, but they can still predict certain behaviors of, well, we may not be able to predict where exactly it will go, but I think we could be able to predict the regions where it could go, like most of the chaotic systems, right? Like you can not predict exactly where the microstate gonna end up, but you can predict the collection of was like a family of solutions that it could go into.
It's actually interesting that you bring that up, because when I was hearing about how you're talking about how hail forms, one of the things that came to mind is geographically what a region looks like that might allow for hail to form in such large quantities. And kind of similar to what Pheely brought up, seeing how plastic travels across the oceans and being tracked by having so many examples of where things end up, it might not be too dissimilar that if you kind of look at how hail formation occurs, sort of related to the geography of an area, maybe the type of formation that you see from large hail could be easily summed up to, types of things like the rain shadow effect or something in a similar vein.
Yeah, no, there's certainly a big effect on geography that's talked about, but it's very chaotic. So we know the general regions in which you're more likely to get hail. So again, speaking about that hail belt in southern Alberta, where you do have mountains causing updrafts, but even then, it's quite a large region, and it's possible that most of the hailstorms don't really hit very developed areas. It might be farms, which was another aspect that they're looking at. They're looking at the effects of hail on agriculture, but it's a very, very complex system in trying to determine, okay, if we have these conditions, what will form? And there's so much that's not known about it because there hasn't really been a lot of modern research into hail formation and hail distribution and all of that. And so that's something this project is trying to solve, is trying to better predict hail using weather radar and seeing where it falls, how it falls. and maybe taking into account things like geography and kind of geology of the region, and just seeing, okay, if the wind blows exactly at this angle up this mountain, we will get hail here, 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 and here. But as of now, they're just still getting started up.
Coming back to the whole crystal structure thing, I found this paper published in just now, so I haven't really read it, but in 2021 in the Journal of Glaciology, called Texture Characterization of Some Large Hailstones with an Automated Technique. And I'm just going to read off verbatim the abstract because it talks about it a little bit. So the abstract of this paper is that hailstone structures have been studied for over a century, but so far mainly by manual optical means. This paper presents new texture and microstructure data, i.e. crystal lattice orientations, grain sizes, and shapes, measured with an automatic ice texture analyzer, which gives access to high spatial and angular resolutions. The hailstones show two main characteristics. One, they're structured with several concentric layers composed of alternating fine grains and coarse, elongated, and radially oriented grains. And two, they show two texture types with C-axis oriented either parallel or perpendicular to the radial direction. Such textures are compared with the ones observed in Lake S1 and S2 ices, respectively. I'm going to skip a little bit. Blah, blah, blah. I guess that's all I want to say. The rest of it's more so just says basically like no one's done this before. We can learn stuff from it. So it seems kind of like there's two types of ice that the hailstones, at least the ones in this study, seem to look like, these S1 and S2 ices, which I don't know what that means, but maybe someone else does.
I don't quite know what the S types are, but in terms of hail formation, the person giving the talk also talked about that, and it's very interesting because you can get alternating layers of kind of like darker ice and whiter ice, and the whiter ice is actually formed from air being trapped inside as it's freezing. So it's freezing quite quickly, where it doesn't have time to let the air escape, and so or the gases inside escape, so it forms this very white ice that almost looks like snow just because of that air trapped inside.
Yeah, I think the ice scientist people out there, under different conditions, you can have all different types of ices with different crystal structures, and they have labels. So I think S1 and S2 are just some specific crystal structure of ice, and I guess hail seems to be primarily composed of those two. And again, maybe this is hail in some specific part of the world or something. I haven't fully read the paper, but it's an active area for sure.
Yeah, no, it's very active, and it's exciting to see that this kind of prediction is getting started up. It's kind of surprising that it was shut down as far back as 1985, the main research project looking into hail. So it's been almost 40 years since it's being actually well researched, and it sounds like there's a lot that's not known. So if you're interested, go check out the Northern Hail Project from Western Ontario, or Western University. And I know they're also recruiting people. So if you're someone who's a student looking for work, anyone from high school and up, they are recruiting to work on this project. So moving on from our intro topic of hail, let's move on to our main topic, which will focus on David's research. And I believe Pheely will be giving a quick introduction.
Well, so I met David at Queen's University here. So he's a PhD candidate, as Patrick mentioned before, in the Crystalline Material Chemistry Group with Dr. Peng Wong. And basically, I think the group has two focuses. First is more like a solid state chemistry, which studies structure and physical properties of crystalline compounds, liquid scintillators for ionizing radiation and subatomic particle detection, or the discovery of novel inorganic materials. There's a lot of words there, but bear with me. The second focus is the materials chemistry, which focuses on crystal growth of semiconductors, energy conversion materials, optoelectronic materials, and X-ray and gamma ray detectors. So those are a lot of science words. But so, David, what exactly do you do?
All right, so it's a really wordy subject. So as a chemist, my primary part in the project is the growth of semiconductors as crystals. The reason that we do this is because they function well as detectors for ionizing radiation. Now, I don't really work with scintillators too much, but semiconductors is absolutely where I work. Specifically, I'm working on a material called cesium lead bromide. It's essentially just a salt, the mixture of the three elements. And it can be grown as a crystal and used to detect ionizing radiation, essentially. That's the brunt of my project.
So when you say detect ionizing radiation, I guess I'm imagining there's like a chunk of this salt, this cesium ionide bromide. Was that it? Sorry.
Cesium lead bromide.
Lead bromide. Sorry, I got it wrong. So just like you have a chunk of that, you shoot it with ionizing radiation, and how does it detect it? Does it emit a specific wavelength of light in response, or?
So as a semiconductor, when it interacts with ionizing radiation, it's actually producing charge carriers. If it was producing light, it would be a scintillator.
Yes.
Yeah. So essentially, by depositing metals onto the surface of this material, whenever ionizing radiation interacts with it, it produces a pair of charge carriers. So if you place that material under some sort of applied bias, you can then collect those charge carriers as a signal.
Mm-hmm.
What do you mean by charge carriers?
Holes and electrons.
Yes.
Oh, it's like semiconductor charge carrier. Okay, like holes and electrons. Like,
That's right.
Okay.
Yeah.
And you work in more experimental side of things, right? So do you do more like a synthesis of the material itself, or like what exactly is that process?
So easily enough, cesium lead bromide can be made from mixing cesium bromide and lead bromide. And it's quite as simple as you take the two, you rub your hands together, and it just pops out. One of the big problems with that is that cesium bromide and lead bromide, just bought at very high purities for this kind of thing, is very expensive. So part of my project has actually been working on a novel synthesis to make this from much cheaper methods. Essentially sourcing the cesium, the lead, and the bromine from various things, and kind of working in a way to dodge a lot of those costs of making really pure things, but still being able to make really high quality crystals for this purpose.
Well, so why would someone be interested in ionizing radiation?
Honestly, this is a great question. When I first joined this lab, I thought it was a really cool idea, but I didn't really understand why this would be such a big deal. Like, why would you want to detect gamma rays on a regular basis with shiny crystals? It turns out it's actually quite useful for things such as airport security, for homeland security. It matters a lot to know where radiation is, when it is, because it is very dangerous to most people. And there's a big market for that, especially with security in the United States and so on.
Maybe in like nuclear power plants too, for like detection of things. I mean, they probably have things in place to detect ionizing radiation there already, but maybe it has applications there too. Who knows?
I'll ask a couple more in-depth questions later, but I'm imagining some applications in particle physics as well.
Yeah.
For detectors trying to figure out what particles are actually interacting. And I'm curious, with what you're developing, if it's able to differentiate between different types of ionizing radiation. Whether it's charged or... Yeah?
Yeah. So alpha particles and gamma rays are the two big ones that you want to be able to detect. Alpha particles are a bit not nice because they don't really go through many things. You know, you kind of just use it as a metric to see if you are making charge carriers that show up as a signal. Gamma rays, on the other hand, show up very nicely. They have a very distinct energy, very high energy. So if your material is able to detect, you will see it. The only problem is because they're really, really strong, they can just go straight through your material. Sometimes you need to apply really high voltage, or maybe you need a really low voltage. Sometimes there's a lot of noise involved. They can be really finicky, but yeah, they can distinguish between the two of those things.
So do you work with radioactive sources to test these crystals then?
I do. Yeah, I use the sources in physics, actually.
The americium?
Americium for the alpha particles, cesium-137 for gamma rays.
Nice. I remember you gotta have like a different radioactive training separately too, right? That's fun.
It was pretty interesting. I still don't really like working with gamma sources. I just feel like I'm hurting myself. It doesn't matter how safe it actually is having sealed source training. There's just something about having it sitting right there bothers me a little bit still.
So in terms of the process that you used to actually create these materials, can you walk us through it? Because you said it might be as simple as just rubbing your hands together and making the two, but you're trying to actually synthesize these materials in a better method. So what are the details of that?
So the first big thing is, if I could just make cesium bromide and lead bromide, then I'm back where I need to be and I could just rub my hands together and form it. The problem is making the bromide salts is a little bit difficult. Now, none of you guys are chemists, right? You're all physicists. So the general idea is you want to source cesium and lead from something and then essentially mix it with hydrobromic acid. That's a very simple source of bromine, right? It's a liquid, you mix it with a powder and you form another powder. The problem is that hydrobromic acid is a very, very low pH, which means when you're trying to make really large crystals, the crystal sizes that we make are on the orders of like 0.5 kilograms. You're producing a lot of acid, which will make a lot of corrosion. And if those metals get into your crystals, they don't function properly for a whole host of reasons. So the general idea is take that acid, mix it with your cesium source, mix it with your lead source. And then when you mix the two of those things together, you actually end up just crashing out this powder, which is the cesium lead bromide. It's actually a really beautiful, nice orange, and it just forms. Most of the logistics comes with the fact that it's sitting in acid, and you need to manipulate it in certain ways to make sure that you can actually form crystals instead of just corroding everything that it touches.
Well, what's so special about cesium lead bromide? Because I guess because you want to detect ionization from these things, so it must have some kind of band gap that is unique or just useful in the range that's useful. Can you have other substitutes other than those materials?
Yeah, so this is a really great question. Cesium lead bromide is really popular for not only radiation detection, but just semiconducting in general, because the band gap is rather large. I think it sits around this is kind of embarrassing, I don't know this offhand, 2.3 electron volts, 2.5 electron volts, somewhere around there. Essentially, it's large enough to a point where it'll insulate without any applied voltage. And then once you apply a bias, you're able to conduct through it. So if you hit it with radiation, you'll see it. A lot of other things are how fast charge carriers move within the material. So a big deal turns out, whenever you're bombarding a crystal like this with radiation and you have an applied bias sitting over it, you're pulling holes to one side, electrons to the other side. If they don't move at the same speed, then you actually get buildup of a charge carrier near one contact. And that causes a lot of issues in terms of detection efficiency over long periods of time. Cesium lead bromide has roughly equivalent mobility between the two. So they just get pulled out evenly, they're able to annihilate each other, and you don't see any long-term effects.
Well, to clarify or elaborate on when you talk about electron and holes, for those who don't study solid state physics or chemistry, it's like it's a weird thing. How do you describe it, Liam? The way I see it as, semiconductor is this material that it has you have two sides of it when you make it, let's say an LED, for example, like the P and the N, and one side you can dope it with a certain material, and you could say that one side has more electrons, and the other side, the other state, it can have the lack of electrons, so we call it holes. So when there's electrons come in, it fills those holes. This makes wonderful things. Liam, how would you describe it? I think I have a terrible way of describing
my analogy that I just thought up, and someone probably thought up before me, is if you have imagine a school bus, and you have a bunch of children on the school bus, and imagine that there's just one kid on the school bus, right? And they hop around between seats, so they just get up and move to the next seat, and they get up and move to the next seat. You can track them as if they're a single unit, like a particle. But you could also imagine that every seat's full except for one, and one random person will get up and go sit in that empty seat, and then they leave their seat empty, and then someone else gets up and leaves their seat and goes into that empty seat, and now their original seat's empty. So even though there's no one in this empty seat, the empty seat moves around as people swap seats as if it was a particle. So that's kind of like a hole, is that you have all these atoms, they're all kind of in a lattice, and you dope them. And I'm not an expert, so I'm not going to talk about it much, but you can imagine that you have like an extra electron floating around that moves around freely. It's kind of like a conductor, where in a metal you have a bunch of electrons freely moving around. This is a semiconductor. Maybe you only have a few free electrons, but you can also add in certain substances such that you don't have extra electrons. You have a few missing ones. You have a few holes in the electrons in your lattice, and they other electrons will fill them, and then they'll leave holes where they used to be. So you get these holes moving around as if they were particles. I'm not a solid state physicist. That's just kind of what I remember from my undergrad.
Yeah, it's kind of hard to put into words, right? But
Yeah.
essentially what it is, like the absence of electron that we can artificially induce into the material, we just call them holes.
And they behave like an electron, but with a positive charge. So they're kind of like an anti-electron.
But not a positron.
Yes. Well, that's
Well,
a little,
I mean, we don't think
tricky.
of it as a positron. It's a trick. It's a mental trick, intellectual trick to think about this system. It's not a physical particle.
It's a quasi-particle. We've talked about this before in the quasi-particle episode.
And we've also talked about conductors before, so go ahead and check out both those episodes, which are in our library somewhere.
Hidden.
So one term that I want to ask you about, David, is optoelectronic. Like, what is it? Is it like optics plus electric?
So I'm going to be careful here because I know that the word optics means something pretty significant in physics. When people say optoelectronic in solid state chemistry, they usually just mean materials that are able to interact with light to produce current in some way.
Okay. You have any example of those type of material?
I mean, so the semiconductors that I described would function according to that.
Mhm.
I believe scintillators fall into that class as well, because obviously it's not as simple as just photon in, photon out. There's something going on in the middle there.
So it's like a photoelectric effect. Whatever material can do that.
It doesn't necessarily have to be the photoelectric effect. There are many other different ways that light interacts with materials. It almost sounds like my comprehensive. I don't remember the other ones. But even outside of the photoelectric effect, things can interact with light in a multitude of ways, whether it forms other photons, it forms only charge carriers, dissipates as heat through phonons, etc.
I see. So basically, you're making this material where you want to, well, in a way, the theory of the material that deal with ionizing radiation is already kind of set in stone-ish. Your work is more into the synthesis of the material.
That's right. So I focus a little bit more on the engineering of trying to produce this material in such a way that I can reduce the cost but maintain really high efficiency. The material is well understood. People don't really know how to make it as super great radiation detectors, but part of the project that I have is showing that it can still work in a very like a large amount of different ways, where you can, save a lot of money and still produce very not just high quality but really clean, really pure material as well.
Yeah, one thing I want to ask about, like, into purity in chemistry. I think in physics, I don't know, I don't deal too much with purity because maybe I do theory and everything can be 100% pure in my equations and my computation. But in terms of purity, when something is pure in chemistry, do you mean like 99%, or you counting like parts per million of contaminants? Like, what do you mean by something that's pure?
So purity is typically described in parts per million scale in the work that I do. When it comes to purity in general, as a concept in chemistry, it entirely depends on what you're trying to use. If you choose to buy materials that are so-called pure, there's usually a range of purities over which you can buy them, just described by how many nines exist in the purity, right? So a 2-9 material is 99% pure, which is usually not considered very pure, whereas something more expensive, for example, for the use of what I would typically be doing, would be around 6 to 7 nines.
When you dope a semiconductor, sorry, maybe a little unrelated, but I mean, we took a class on it before, maybe 2 classes, I don't remember, but I know semiconductors aren't pure because you dope them, you put other things in them. How pure would a semiconductor, or the one you're working on at least, be? How much is it doped?
So
I guess,
actually,
what do you?
I don't dope my semiconductors at all, actually. The concept of doping semiconductors to reduce the purity in a known way is known as something extrinsic. It can be used to modify the charge carrier inside of the material, right? If you want to make it more electron heavy or more hole heavy.
Okay.
In the case of taking out dopants or just not putting any in, it's known as an intrinsic material. What I work with is intrinsic. I don't actually need to modify the charge carriers.
That's weird because it's like when you get taught it in your physics undergrad, at least, it's like one of the core components is that it's doped. No one ever mentions that these intrinsic semiconductors exist.
It's a pretty cool idea.
It's probably well known in the community, but someone who's not in that community, I've never even heard of that. That's cool.
So in terms of actually measuring the purity of these semiconductors that you're producing, how do you go about doing that? Is it like XRD, or is it something else that you're using, a different technique?
Yeah, so XRD, interestingly that you bring up XRD is really good at determining phase purity of a material. So actually, we were just talking about ice. If you look at the phase diagram of ice, there's a ton of different structures of ice that exist, even though it's just H2O. Similarly to that, the material that I work with and many other semiconductors can exist in different phases, depending on how much of each certain element you have in there. That's the concept of stoichiometry. XRD can tell you whether or not you have good phase purity within a material, but if you're looking for small amounts of contaminants on the order of dopants, for example, it won't be able to tell you that because it can only really see roughly about 5% of the material before the resolution gets too low. So to look at part per million impurities that exist in material, you have to look to techniques such as ICP-MS, which would be mass spectrometry. That would be the idea of digesting your material, looking at the atoms that come out. Specifically, we use solid state mass spec. So rather than digesting it, you actually stick it into a block of molten indium, and then you just vaporize it in a vacuum chamber. And it'll give you really, really good resolution of part per million impurities that exist in your material.
Oh, it makes sense though, because the X-ray diffraction actually, well, they try to measure the crystals in like geometrical structure, right? It doesn't tell you what are the outer material in there, because it basically you see the diffraction diagram, basically like a projection of certain planes, right? That's why you shoot X-ray diffraction in certain planes to hopefully figure out its Miller indices and all this reciprocal space stuff. But it doesn't tell you if there's outer material in there. It just tells you if it is a certain crystal structure. While match spec is basically like, I think it's a light-based system, right? It's like where, or maybe it's not light-based, but it tells you, well, what elements are in your material. And if you know if it's cesium, lead, bromine, if there's something else that's not cesium or lead or bromine, then it's not as pure.
And actually getting back into the dopant idea, having an idea of what is in your material that isn't cesium, lead, or bromine can give you an idea about how it actually manipulates the electronic structure of the material as well, right? If you have something like iron that's sitting in there with a lot of electrons, you might actually be seeing an issue with too much charge carriers of one type existing in your material, and that leads to a whole host of problems as well.
Accidental doping.
So when you so you want to create this tool to measure the ionizing radiation. Well, how good is it compared to other methods? And what are other methods that are around to deal with this type of detection?
So in order to detect ionizing radiation, the material that I make is not up to par with industry standards. I'm a grad student. I'm not an engineer who's working out in the field. So I think that's expected. In terms of industry standards, typically things like high purity germanium are used. I know they use that a lot in large underground labs, for example. It works really, really well. Typically, the metric that we use to see how well you're actually able to detect radiation is a metric known as resolution. It's essentially whenever you see the energy of some specific type of radiation go into your material, it should correspond to one type of charge carrier pulse coming out of your material, right? Energy in, energy out. Obviously, that's not the case, and you get some sort of broadening. Depending on how broad that kind of change from light to electricity is, determines how good you are at seeing radiation.
I mean, I've used a germanium detector in labs as I teach the fourth year one. It's fantastic. Like you can see exactly that the spectrum is really clear. The band is really narrow, and it to me it looked like a chunk of metal, but apparently it's very expensive. But so okay, but it's very expensive, right? Like germanium to make, and I think. And you also, I think some of them you have to even put it in like really cold temperature to make it work really well because there are a lot of noise. But so does your crystal, because it's semiconductor, it doesn't have to be cold, or does it?
Yeah, that's exactly right. The biggest benefit of using the salt that I use is that it functions at room temperature. There are other materials that function at room temperature as well. Germanium is not one of them. Silicon, I believe, also doesn't do that. Silicon is also quite light. It doesn't have a lot of electrons in general, so radiation tends to kind of just go straight through it. But when it comes to other types of materials, my material is able to function room temperature, ambient pressure. All you really need is metal on the top and bottom, some sort of electrical contact, and exposure to radiation. And as long as you're able to bin up those pulses that come out, you should be able to detect.
Right. So for application in more daily life that's more appropriate rather than like, well, every detector has to have 5 liters of liquid nitrogen at every station at the airport. That's gonna be ridiculous.
Exactly.
So I think this get to a point where we usually pivot into your life a little bit. So tell us how do you get into the interest in this project in grad school? Were you just looking around at the end of undergraduate and found this project interesting, or was there someone like whisper in your ears about the project? How do you come about get into this specific field in grad school?
So my undergraduate's from the University of Toronto, and I was always focused in materials chemistry. Nothing specific about semiconductors or radiation detectors or whatever. I used to work in quantum dots, but my biggest interest was how light interacts with matter, essentially. I thought it was a really cool facet of how matter functions in general. And as I went through chemistry, I found I was always kind of getting away from chemistry. I was always a bit more focused in the engineering and the physics parts of chemistry, even though I wasn't in physics or engineering. So when I came to Queen's for grad school, I had a few offers from some professors. There were some solar cell labs that wanted me to come, and I wasn't super interested in it because solar cells are kind of, everybody does them. When I heard about the specific field and being able to kind of take the knowledge that I learned from inorganic courses in undergrad, it seemed pretty applicable. I kind of just wanted to go and test the knowledge that I had to see if I could do something that actually amounts to so-called real research in grad school. And that's how I ended up there.
Right. So I'm gonna walk you slowly down the memory lane, right? So you get into grad school, but before that, in undergrad, what got you, into chemistry? Like was it always your thing that you were gonna do chemistry undergrad, or maybe were you always a chemistry student? Because some people started off in other major or program. Like, what was it like your discovery of your love in chemistry?
So I wish I had a really nice story for this. It's actually pretty stupid. I wanted to go to school for chemical engineering, but it's really expensive. And I thought, hey, chemistry is pretty cool. And it's probably not too dissimilar. So I went into chemistry. In terms of why I picked chemistry, I had good grades for it in high school. And I thought it was actually pretty interesting, but only because I was working with a lot of thermodynamics and stuff like that. Never really did any organic chemistry. I didn't really enjoy that. But it worked well for me. And I saw a bit more prospect in it than I did in physics at the time.
To be fair, most of my friends who took organic chemistry, I don't think, well, from what I heard, it's not the most enjoyable course.
most people I know who did chemistry, they don't like the thermodynamic parts of it. And they like the rest of it more. So it's interesting that you were
That's kind of
the
how I
opposite
ended up in
too.
this field in the first place. Even though I am a chemist by trade, the work that I do is very, very different than a lot of other chemistry people. A lot of people, they work on small molecule discovery, drug discovery, stuff like that. Even more into like green chemistry, working with enzymes and things like that is definitely more popular than the kind of field that I work in. But I love what I do.
So keep walking back down,
That's
right?
what matters.
And was science always your thing? Like here's the thing about journeys for different people is that some people are like Liam is a little bit of a late bloomer in terms of science, right? When he found the love of it in high school and such. Or some people were like, they know since they were 7 years old that they really want to do science. What was that like for you? Was it always when you were young, someone sparked your interest? Was it any idol or thing that you look up when you grow up? Like, what was that like for you?
I can't think of any specific idols that led me into science. I definitely was always a science person well before high school. I think going all the way back to like being 5 to 6 years old, I was always more interested in like space, dinosaurs, but more for the reason that they are things you can look more into. It was interesting tangibly, but looking into it further, learning about the planets and they have different atmospheres and they're way out there in space. It was always intriguing, and I wanted to learn more about that kind of thing. Not space in particular, but just in general, being able to dive deeper into this kind of thing was very rewarding for me.
I think, yeah, that's like a scientific curiosity, right? Like when I think most people would have it, but fewer would choose to actually go to the path, go to all these complicated way to actually understand or comprehend this very complex system. And was it always supported as a career path? Because at least for me, like physicists in a developing country, we don't have that much funding. That here it's not doesn't sound like a proper career path. Well, because you grew up around Toronto, right, in Ajax, and was it always a thing where like, science as a career was good?
No, it was I never really thought about it as a career style thing until I decided to go to university. Prior to that, it was just something I enjoyed. I mean, I went to high school, science was always my favorite subject, chemistry and physics by far. And when I realized I need to pick a specific major when I'm going to school, I really wanted to keep in mind the fact that I am going to school ultimately to get a job at some point. Now, you can call it naive that I didn't pick physics because there are tons of jobs in physics, obviously. But at the time, when I was thinking back, I honestly wanted to be an astronomer at some point too, around that time. But again, when I was thinking about job prospects, the first thing that came to mind is there are a lot of people who interact with chemistry in like a lot of jobs. When it comes to drug discovery, making of cell phones, making of any kind of electronics, really, it seemed really or not simple, but the connection was very easily available to me at that time. And I guess that's what influenced me to pick this.
What really what I think about chemistry is much more practical. So in a sense, to physics, one could argue is practical, but in terms of theory of physics, the only thing that we understand and then describe well is the hydrogen atom. The rest is approximations, right? And the chemist has a way to basically do the mean field thing or describe thing in term averages or valence, and doesn't have to go through how electron interact quantum mechanically, but still be able to describe real world chemical reactions and such without having going through the operators and probability system and such. So in a way, chemistry is much more practical in a sense of when you sit down and do a chemical experiment, it's like, well, you create something you could see. That's what I find in like high school chemistry. Like, you make the flame green because this is the reason why. You have to solve the quantum mechanical system to have the description, right? And what's fascinating about chemistry is that part. You probably do titration for people who study science, right? And you can clearly see what happens. rather than when you go look at oscilloscope for certain interactions, like electronic interactions, like, oh yeah, there is a peak, it's Lorentzian, but you don't see it as a real thing. You see it from the screen.
As a theorist, the oscilloscope is like my version of that. It's like you do something and then it creates a waveform. You're like, wow, it reacted to something I did.
Yeah, no, I think you're totally right. I mean,
yeah,
chemistry is just applied physics at some point. A lot of it is simplified to a way that can be used much more practically. If you ask a lot of chemists, what an electron actually is, some might actually say a little ball that spins around a nucleus. It's not what people tend to focus on. Not saying that all chemists are like that. I don't think I'm like that. But at the end of the day, it's kind of what drew me to it a little bit more.
Yeah, and there's nothing wrong with that. Like I had two really good high school chemistry teachers. And one of them always made this analogy when we were talking about, you learn like the periodic table and your sp df orbitals. And he said, it's like, you don't need to know how to fix a car to drive it. I mean, if you know how to fix your own car, that's great. But he would tell us like, here's the S1s, and here's how you label all of them, and here's all the numbers, and people would say, well, where do they come from? And he said, if you want to learn about that, go spend the next 10 years of your life doing physics.
You don't, in that analogy, you don't even need to know how the car works to fix it. No, like, even mechanics, like,
no, you just bring it to a mechanic.
They know how to fix it, but
right.
But I think, well, some of them knows how exactly the thermodynamic cycle work of the engine, right? But you don't need to know that to fix it. Like, if I fix a toy car, I don't need to know exactly how battery is being discharged. Like, what exactly are the material of the battery? So how does that system work, right? But there's a different resolution of understanding you need to be practical. And those I find about, like, let's say engineering in general, right? They understand how it works in the engineering way, I think, which is extremely practical. And they need to do that. But if you have to go into like the hydrogen atoms every time you try to fix a car, then that's more like a physicist's dilemma.
Yeah, well, I mean, I don't. Not every you don't need to know how to fix everything in your car because someone can do it for you. And then not every car mechanic knows about thermodynamics and all that stuff. And it's the same thing with chemistry, right? Like, you can do really, really good chemistry and you don't need to know about what's going on in the background. That would be honestly a waste of your time, probably, to try and understand that when you don't need it. It's important sometimes, but not all the time. So, and just even going a step further, you don't need to understand all the quantum field theory going on behind the quantum mechanics that's going behind the chemistry. There's layers. Everything is an ogre.
So we got into your life a little bit, into what got into your science. And, I find that every time I talk to chemists, we have a lot more in common in terms of the material or what we know. But it's almost like it's a different resolution. Because to me, it's the same perspective, because it's like, let's say we look at an atom, like chemists care more about the valence or electronic structure, because that's where all the chemical reactions are, right? They're not nuclear. And physicists more like look at a system in a different resolution. We're like, well, what do you mean electron? Oh, what is an electron? What is a proton? And how does this system come together? And I wonder, in your experience, when you study chemistry, especially like because I never took graduate courses in chemistry, are they more on the electronic level, on like a chemical reaction level, or the graduate course in chemistry actually go into, let's say, the quantum mechanics of things, how actual chemical reaction form?
From what I've heard, I'm not a chemist, so I'll let you speak, but you have like one or two classes on physical chemistry, on like the Schrodinger equation and stuff, if you want to take it. But I don't think it's, depending what route you go, you might not take it. I don't know.
Yeah, I think you're right about this. I mean, to answer your question, Pheely, chemistry courses will depict things depending on what's most applicable to what you're trying to study. So in my experience, taking a lot of graduate courses in solid state chemistry, solid state mechanics, you do have to learn a good amount of quantum mechanics. I've had to take statistical dynamics before. I've had to do a lot of things where the depiction of things like atoms do focus on, the makeup of nuclei, kind of how particles work. But if I were in a different field of chemistry, like say green chemistry or organic chemistry, you'd be looking at it from a bit of a farther away lens, looking at not so much how electrons kind of exist in certain orbitals or certain energy states, but more so, how do atoms link together to form reactive kinds of groups, right? How do large molecules bind to each other so you can make different kinds of drugs, right? Chemistry is very, very broad in that sense. There are so many different kinds of chemistry. So the type of things that you learn as you move forward in chemistry are heavily dictated by what you specifically want to do. It's probably not too dissimilar from physics in that sense, right? Like just because you're a physicist doesn't mean you know everything about astrophysics, even though it is a part of physics, I think.
Yeah, for sure. I feel like chemistry is definitely more broad, though, I'd say. Just because you can do things like you can do like quantum chemistry where you're partially a physicist, or you can do like chemical engineering where you're partially an engineer. So yeah, like what you said, depending what you do, you can go in either direction and probably other directions. And in physics, it's definitely similar because like you can do like medical physics, right? And you can never look at quantum mechanics or relativity in your life. But then you're borderline like chemistry or biology. I find physics a bit more narrow than chemistry, but maybe I'm coming at it from a very narrow viewpoint.
I think you're right, actually. I mean, chemistry does have a lot of broadness to it. It's funny, too, because the group that I work in to do this kind of research is actually mostly comprised of physicists in the chemistry department or engineers. I think maybe 2 of us are chemists. And it's weird because even though we have such different backgrounds, we're able to actually kind of come together in this big hodgepodge of chemistry, physics, and engineering. And it takes a little bit of each of those fields to kind of come to an understanding of how these kind of things work.
Well, and also like, classification and categorization are arbitrary. There are knowledge of the world that we try to figure out. There are complex systems that there's only one nature, there's only one nature. We just study things at different scale. We name it different things, and we form factions and tribes, and say these things about physicists, chemists, and
Booga booga.
Yeah, engineers even though we do different things, but in terms of spirit of scientists, we basically try to do the same thing at different scale, at different resolution, at different philosophy, and that's why when we have multiple people from different fields on this podcast, but one thing that I find that we all have in common in this scientific curiosity, no matter what we are trying to figure out in terms of doing graduate research and such, we do it because we are interested in it, right? And to me, that's the most fundamental and most important thing as for our human life to do. Not in terms of it doesn't matter if you figure out hydrogen atom or protein structure, but as a human being, you're still figure out something. Right, so that I think that's one thing that I wanted to point out. So as we are wrapping up here, so David, so if someone is interested in your work or curious about you or your journey and your story, you prefer any way that they can contact you, email, or we have some who don't want to be contacted either. So if they have questions, they can send it to us and we'll pass it along to you. What was your preferred method?
I mean, I'm always happy to receive questions. Through email is probably the best way. My email is just david.kunar@queensu.ca. I'm also happy to take questions through here, too. If you guys get questions, feel free to bring them to me. I'd be happy to answer.
And just one final question for you, David, because it looks like Pheely, who usually asks it, didn't quite mention it this time. But what are your dreams and aspirations? Where do you see yourself in the next 5 to 10 years? What do you want to do with what you're doing now?
Who do you want to be as a human?
Okay. Yeah, I forgot about that completely because every guest we ask about hopes and dreams, right? So it's like, who do you want to be? Not exactly 5 years or 10 years, but who do you see yourself? Are you going to be a scientific researcher, a chemist? Like, what is that hope and dreams?
All right. I totally want to be in a stable relationship and happy. You know what? If it means I'm not a chemist, so be it. But I love chemistry. I do think I will be a chemist 5 to 10 years from now, maybe even more than that. But realistically, I would enjoy to keep working in science. And, as long as I can make some sort of a living out of something that I enjoy, similar to what I've been doing this entire time, I think that would make me the most happy.
What about academia? Or do you like teaching, or are you more like practical, industrial based?
I definitely feel like I'm more towards that industrial side. I do like teaching, but running a lab in academia is a lot of work and it's a lot of stress. Probably not for me. I mean, my options are open, but I'm definitely leaning away from that and more towards kind of just working within the industry.
Nice.
Okay. Well,
Nice.
thank you very much, David, for talking about your work and your aspirations and your past and really answering our questions. Apologies if it did feel like a comprehensive exam or candidacy exam. We don't mean it to, but we are very grateful that you could be on our show.
Yeah, thank you guys so much. I mean, great questions. I had a great time. It was awesome speaking to all three of you. Thanks so much.
I was going to say, don't tell the physicists, but my favorite guests are always the chemists. We've had 2 or 3 of them, I think. I can't remember now, but we'll get some more on.
If you would like to be a guest on our show, we have many ways in which you can contact us. You can reach out to us over email. We are hyperthesispodcast@gmail.com. You can send us an email with comments or questions. If you'd like to reach out to David through us, we are more than happy to relay any questions or comments along to him. Unless they are really mean, then we'll keep them to ourselves. But I'm sure they wouldn't be. If you also have any other questions or comments or want to contact us, we have an Instagram. You can find us at the Hyperthesis. We post updates about when we post episodes. So you'll see maybe a little brief glimpse into David's work in life through our Instagram post for this episode if you haven't seen it yet. So make sure to give us a follow there, subscribe, or whatever you do on Instagram, and leave a comment, and also reach out to us over DM. We are more than happy to receive messages from people, especially if you would like to be a guest on our show. If you are listening to this, congratulations, you made it, you found us. And if you would like to continue listening to us, we are based out of Spotify, but we can be found on pretty much whatever podcasting platform you use, whether it's Google Podcast or Apple Podcast, Audible, truly whatever you use, we are there. If you really can't find us, but you're still somehow listening to us, you must have found us on YouTube. So we do have YouTube videos. We are pretty much caught up, I believe, thanks to Pheely's hard work and his Mac's hard work in rendering and creating those episodes. That Mac is just a workhorse. It's crazy. This is not an advertisement for Apple, although you can listen to us on Apple Podcasts, and you can watch us on your Apple computer or iPhone or whatever device you use on YouTube. So you can subscribe to us, leave a comment, leave a like, and you can reach out to us over there. And again, just for David, if you'd like to reach out to him with any questions, his email is david.kunar@queensu. Oh, sorry. I had Weston on the mind. Yes, it will be in the description, so go ahead and check that out, as well as links to episodes that we have mentioned and other material. Now, to end off the episode, we have a nice story from Pheely.
All right. So today, because we were doing some talk about materials, so I figure I should talk about, actually my favorite thing to learn is military technology. And so this is how the protection of tanks has evolved throughout the years.
Ooh.
Yeah. So at the beginning, when tanks joined the World War One back in those days, they're just heavily armored, right? And the anti-tank rifles relied on basically the speed and the mass of the bullet, or basically the momentum or the kinetic energy of the metal shell to pierce through the armor. And so to protect the tanks in those days, they make the armor of the tanks thicker and thicker. and that makes sense, right? So it's not being penetrated. However, it also makes the tank much heavier. And what people came up with the way to deal with tanks are those grenades, right? Using the anti-tank grenades. So during World War II, the Soviet developed what they call the RPG-43, basically an anti-tank grenade, where the RPG does not stand for rocket-propelled grenade like the popular belief. It's actually a backronym, which is a backwards acronym because the Russian language is different. Right? It basically means handheld anti-tank grenade launcher. So for RPG-43, it looks like a stick bomb if you play the good old, Call of Duty World War. There's like one the stick bomb that you throw. That's for the tank. And they have something like the tank mine for the tank to penetrate from the bottom. And later on came with like the projectile launcher, like the bazooka or the Panzerfaust, which are basically grenade launcher, while the bazooka can be reloaded, but Panzerfaust is disposable.
There's some other weird and wacky ones, I think. Like I think there's one that's basically a spear, and you have to like basically hold it against the tank when you use it, which is obviously really dangerous if you're a soldier. If someone hands you this weapon and they say, all right, walk up to that tank and blow it up, it's like, well, I'd rather do it from far away, but okay.
Well, yeah, that's one of the problem with anti-tank weapons back in the day. Is like the RPG-43 weighs up to 3 pounds. So if you're going to throw that from afar, that's going to be quite difficult. And so that's why they develop launchers where you can just park somewhere or go a little bit further and shoot it to the tank. However, so after those launchers come the RPG-7, which is probably, it is the most widely used anti-tank weapons in history. And that is what you think the RPG is when you hear RPG. That's little stick you put on your shoulders and shoot out the grenade. That is RPG-7. So this RPG-7 rounds actually special. So it's called the special type of explosive charge known as shaped charges. And for the rocket-propelled variants, like little rocket, there's the metal liner form this kind of cavity that looks like a cone, and the explosives are packed behind that liner, which is as metal. So when hit with a target, people I think usually think of RPG as just the explosion, like a spherical explosion, it just explode, but it's not exactly what it's designed for. So when the charge is detonated, the conical shape of the explosive and the geometry of the liner create this pressure wave behind the liner that deform the liner in a way that it actually creates this jet or this line of like this concentrated metal that propel into, it's like puncture as a little hole. And because it's the explosion is concentrated into that hole, it's like a stream of metal jet that puncture small holes into the thick armor really well. And what happened when it's come to the other side of the armor, it expands, right? And all those momentum and energy comes out and it kills whatever is inside and possibly explode the ammunition inside the tank. And that is how and those like hypersonic speed jet of metal particles basically kill everything inside. So when you see the explosion from the RPG from the outside, it looks like a big explosion. But what is lethal is those metal jet streams inside that puncture the hole. So it's basically the energy of the jet that penetrates the armor, and this kind of devastating explosion or like puncture kills everything that's inside. However, modern tanks are created or designed to deal with that too, because they realize they want to puncture it. And I think one of the motivation is this little piece of history from the Philippines. And when they were in the 2017 the city of Marawi in the Philippines, for 5 months it was a battleground where they I think they fight with the terrorists which identify with ISIS. And what happened is that they don't have modern tanks or any fancy tanks, but the RPG-7 is so popular, or even RPG-2 and a former form of this hyper explosive were widely used by the terrorists. So what happened is that instead of they don't have that many tanks, but they have vehicles that can be destroyed by those RPGs. So what the ingenious way they come up to deal with that? They put cardboard and planks of wood on the side of the vehicle. That's like, okay, that's not going to protect from the RPG. Sure. Here's the thing. The RPG can puncture thick armor really well. However, if there's a gap, if I put a wooden plank in front of it, it would penetrate the plank really well, but it would not penetrate the armor. So they actually put cardboard and planks around the vehicle, and it does protect them from the RPG. It's a little funny, isn't it? Like, it can puncture really well, but if you has a gap or another material which is soft, doesn't matter, right? It's cardboard. But the penetration, just because you increase the thickness with whatever material, it actually protects you. So, however, in modern anti-tank weaponry, they actually explode twice. They actually accounts for that too. So it's very difficult to deal with. So what I want to actually talk is the explosive reactive armor. So instead of having those wooden plank and such, so we're gonna have this explosive that's really hard to explode. It actually, what's it called? It's actually inert. So it takes a lot of energy to make it explode. And it's a controlled explosion. So when you see the tank with a bunch of boxes around, it looks like armor, but there's a bunch of boxes around. Those are like explosives. So, for example, C4 is one of those inert explosives. It's not going to explode by putting a lighter on it, right? So it has a specific energy for it to explode. And what it wants to happen is that once you get shot by an anti-tank explosive, it would explode and destroy that pressure wave. So that small explosion wouldn't be able to penetrate the armor, but it would protect them against the highly concentrated pressure wave that would come out of the RPG or the anti-tank missiles. So that's why when you see the modern tanks, they have these little boxes around that those specialized inert explosive to protect the tank. However, like I said, the modern anti-tank, like the Javelin and such, they explode twice. So the first one to destroy those inner explosives, and then the second one to puncture the armor. So there's this back and forth of technological advances that try to either protect the tank or destroy it. So I know where it's going to go. It looks like the anti-tank is very effective from the recent war. As you will see, there's these handheld machines. However, those are also Soviet Cold War era tanks. Modern tank has different capability. But that is a story for today, how people devise an explosive to put around a tank to protect it from auto-explosive.
I always have mixed feelings about guns and things with war because, obviously I think killing people is bad. But from like a physics standpoint, guns and tanks and planes and missiles and all that stuff are very, very interesting to me. Like the amount of genius and cleverness that goes into designing these things. Like, just putting planks of wood and cardboard on the outside of yourself to protect your vehicle. Like, that's ingenious, right? It's the same thing with like industry, because I live in Hamilton, so there's a lot of smokestacks and flames shooting out of them and stuff. Like, it's bad because I want to save the environment, but at the same time, when I drive by it, I'm always like, oh, they just look like big steam engines, and like, I don't know, my inner physics nerd loves it. So I enjoyed that story.
And we hope you enjoyed that story too. So thank you again to David for coming on as a guest. We are very happy to have you. And tune in next time for another episode of Hyperthesis. And remember to get into contact with us if you would also like to be a guest on the show. Thanks for listening, everyone, and bye.
Take care.
See ya. Thanks, David.
Thank you guys so much.